Okay, so we're live on YouTube, and I'll spotlight UJC. Just have my usual small number of steps that I do to set the security on the YouTube stream.
All right, so I'll just wait maybe a few more seconds and then I'll start.
I'll just give me the chance to start the recording as well.
Yeah, sounds good.
Okay, I think we're in good shape. Start whenever you'd like. Thanks, Jason.
Okay, thanks. So hi, everyone. Welcome back to this series of lectures on statistical mechanics of disordered systems. Let me start by reminding ourselves what we have done last time. So last time, we discussed some motivations for the way statistical mechanics presents itself, in particular, how Gibbs measures arise in some generic setting. So the gist of the story is that whenever we give ourselves some energy function, we construct this associated Gibbs measure by looking at the probability measure, which to each configuration attributes a weight proportional to the exponential of some coefficient times this energy function. And this coefficient, I denoted by beta last time, is the inverse temperature. Okay, so in fact, from now on, I'm going to essentially set beta equals 1 if you want, and put the parameters inside the energy function itself. It's just some convenience for my notation. Okay, and then last time we also discussed some historical background on the Ising model, which I think is also interesting in terms of understanding where the field comes from, and also I discussed a bit of the phenomenology of the model. And also I started to discuss a simpler version of the Ising model called the Curie-Weiss model. And for this model, we have a lot of units as in the Ising model, but each unit interacts with every other unit. And so I wrote down the energy function here on the slide. So there are, instead of having just one temperature parameter, I put two parameters. One also encodes this external field H. So I fix T and H. So T is non-negative, H is a real number. And for each fixed value of T and H, I define an energy function, Hn of T H sigma, which is as written on the slide. Okay, so it's similar to the Ising model, except in this sum here, I did not write down that I has to be a neighbor of J. So if you want, everybody is a neighbor of everybody else. Okay, and this for this model, I want to study similar questions as those we discussed for the Ising model, in particular, how the mean magnetization behaves. And we discussed last time that although maybe what we really care about is this mean magnetization, it's useful as a first step to focus on the free energy of the model, which we define in the following way. So 1/n log, okay, and then I fancied to put 1/2 to the n here, but this is mostly for aesthetics. It's not important. So the sum over all configurations of the exponential of the energy function. Okay, and I also introduced notation, which maybe I'm going to spend just one more minute making sure we all understand what this notation is. So this is the expectation. I defined some expectation thing using this angular bracket notation. And so the expectation for this particular bracket measure of f of sigma, by definition, is the expectation with respect to the Gibbs measure. Okay, so it's, if I write it explicitly, it's the sum over sigma of f of sigma exponential of hn divided by the sum over sigma of exponential of hn th sigma. So far, so good. Are there questions on this? It's important that you feel comfortable with the notation because we're going to use it for a long time. All right, and yes, so if just to make sure we see again this point about the derivative of the free energy, I'm not going to write it down completely, but you see that if I differentiate this function fn with respect to h, so h is hidden inside the exponential here, you know, so you should think that you replace hn by its explicit expression. So h appears here. So when you take the derivative, so there's a derivative of the log. So you have, you know, the derivative divided by the quantity itself, and the derivative, it will be, you know, exponential of h sum of sigma I. The sum of sigma I will pop out of the exponential, and you're going to do this sum over sigma of this quantity times the exponential divided by the sum over sigma of the exponential. Okay, and there's also a 1 over n in front. So in fact, what you do when you compute this derivative is computing the expectation of that function 1 over n sum of sigma I. Okay, which let's decide this is what we want to study ultimately, okay? Especially how it depends on T and H. Okay, and yeah, also I bring your attention to the fact that when I define this angular bracket notation, if I was more explicit, I should keep somewhere in the notation that this thing depends on T and H. But because I want to, you know, possibly at some point we will write several times this bracket thing, I don't want to all the time have to put the indices T and H or something. So I don't write it down, but keep in mind that it depends on T and H. So, okay. And now, let me say right away why this Curie-Weiss model is so simple, in fact, to study. It is really simple because this part, which, as Omer said last time, this is where the interactions are encoded. You know, this is where it's not just each sigma appearing individually. We are multiplying two together. This term, in fact, I can rewrite as a function of that simpler term. So let me, this is a very elementary observation I'm making, and I'm just saying that the sum of sigma I, sigma j over all I and j, this is the same as the sum of sigma I squared. Okay, so I'm saying nothing fancier than this. And as a consequence, it will be relatively straightforward to identify the limit for energy of this model, as I'm going to explain in a second. So, yeah, so we want, let me rewrite this for energy. Okay, or maybe I'm going to write just what is inside the logarithm. So 2 to the minus n sum over sigma of exponential Tn 1 over n sum of sigma I squared. I'm going to write like this. Plus h. Okay, maybe I'm not going to write. Okay, I'm going to write n. 1 over n sum of sigma I. Okay, and what I want to try to reveal here is that so this thing you should think of this as being an expectation with respect to Bernoulli. Instead of writing 2 to the minus n sum of sigma I, sum over sigma, I could just write expectation with respect to product Bernoulli measure. Okay, and so it's a the sigma, the coordinates of sigma, you can think of them as being independent and identically distributed Bernoulli random variables. And this quantity is precisely the quantity about which we talked about which we derived large deviations in 2 lectures ago. Okay, so if I ask myself, what's the probability that under this reference measure, this quantity is near M? I know the answer to this question. Okay. So let's say recall from large deviations. Oops. Let's say for every M. So the probability, I'm going to write like this. So I'm going to use this informal notation. Okay, this is approximately equal to M. So you see this notation, you should read that as the probability under this measure that this event occurs. Okay. So this we said is approximately exponential of minus n times psi star as we wrote it, psi star of M. Okay, where psi is the log Laplace transform and psi star is the convex dual. So psi of lambda is the log Laplace transform. So it's a log of the expectation of exponential lambda sigma 1. So expectation here I write 1/2 sum over sigma, let's say sigma 1 in plus or minus 1 of exponential lambda sigma 1. So this is a complex notation to write just log of hyperbolic cosine of lambda. And psi star is the convex dual. And you can verify that its expression is given by the following formula. And in fact, here I'm quoting large deviation, and I'm using these psi star things, but in fact, this is really the exact same result as the one we started with, when we were discussing Bernoulli random variables, except that when we did this initial computation with Bernoulli random variables, I was using Bernoulli variables which took values 0 and 1, and now these ones they take values -1 or 1. So there's just some change of function, change of variable you have to do, but it's in fact exactly the same computation. So you don't actually have to appeal to this big theory of large deviations for the specific observation. You can just derive it using Stirling's formula as we did at the beginning of the lecture of 2 days ago, or I mean on Tuesday. Okay, is that clear? So why do I want to use this? Is because, so let me go back to what I want to compute. This is what I want to compute here. And I can decompose this into the different possible values of this mean magnetization. I can slice this sum into, maybe I take a little epsilon and I say, I insert the indicator function that this mean magnetization is between m minus epsilon and m plus epsilon, and I span the whole interval and I see how things behave. Let me rewrite this sum with the indicator function indeed. So if I look at 2 to the minus n sum over sigma, so I restrict the sum to, so this is an informal derivation. Here later I'm going to prove it a bit more precisely. But here it's just to make it clear what happens. So we have Tn 1 over n sum of sigma I squared plus Hn 1 over n sum over sigma I. Okay, so I specialize the sum to only those configurations that satisfy this approximate identity here. So if this is true kind of approximately, then I can substitute by m in these two slots. And then I'm just, then it no longer depends on sigma, which is inside this exponential. So I can evaluate the asymptotic behavior of this quantity by using this large deviation statement. So here, let me write it like this. So this is approximately m, and here the same. So this exponential disappears, and what we infer then is that this is approximately, so exponential Tn m square plus Hn m times this remaining sum here, and this remaining sum we said behaves as displayed on the top of the slide, like here. Okay, so it's exponential minus psi star minus n psi star of m. Okay, and maybe you remember from this exercise in the first problem set that when we look at the sum of exponentials, so imagine now you're doing this slice for different possible values of m, and you're trying to understand the asymptotic behavior of the entire sum. So the asymptotic behavior will be driven by where this quantity in the exponential is maximized. Okay, so let me write a precise statement to this effect. So proposition. So the limit when n goes to infinity of fn of th. So remember that fn of th is it's the global sum here, okay, without the indicator function, of which we take the log and then we divide by n. So when you take the log, okay, the exponentials here disappear, and then you divide by n, the n's disappear. And so the statement is that this limit is the supremum over M of Tm square plus Hm minus psi star of M. Does it make intuitive sense? So I have not given a full proof here, but I want to postpone the proof to the next section. So today we'll see a proof of this statement, but I want to prove it in greater generality. But at least intuitively, does it kind of make sense? Nobody complains, so I'll take it for as meaning that that it's okay. Yeah, thanks. Thanks for the feedback. Okay, so we will prove a more general version soon. Yeah, the soup comes from the fact that you know, if you have, let's say there are only two possible values of M. So you have the sum of exponential n A, let's say, plus exponential of n B, and then you take the log, you divide by n. When you go to infinity, it's the maximum of these two values which will contribute. You know, if you remember this first exercise in the first problem set, this is the same phenomenon. Yes, exactly. As said in the chat. But if the exact reason is not completely clear, I'll give a proof quite soon. So don't worry. Okay, so as far as the Curie-Weiss model is concerned, we have identified the limit for energy. And so now if we want to actually talk about this magnetization, this thing which I said we can recover by taking the derivative, I have one more thing to do because I want to understand when it is that the derivatives of Fn converge to the derivative of the limit. Okay, so I said before that this is okay, no problem. But today I'm going to justify it instead of just waving my hands. Okay, so I'm going to add one more piece of information. So let's say if F is differentiable in H, at a specific point TH, then the derivative converges to the derivative. Oops. Oops. And I'm not going to write it down, but if it works also in the t variable. If if the function is differentiable in t, and let's say that t is not 0, because if you're at the boundary, okay, bizarre things can happen. Then the same statement is true. Yes. Thanks for this question. F is the right-hand side above, so I should define it. Okay, so let F be the right-hand side above. Okay, I mean this guy. All right, so let me explain how to prove this. So is the statement clear now that I defined what F is? right, so let's prove it. Okay, so the main ingredient is that all these functions we're talking about are convex. Okay, so observe that Fn and F are convex. So let me display what Fn is. It's quite odd. Here it is. So you see that its structure is, okay, so forget about 1 over n. Okay, we're just asking about whether it's convex, so we don't care if there's 1 over n in front. It's the log of some expectation of the exponential of some, a linear combination of random variables. So it's exactly of the form, some time ago in the second session when we discussed convex analysis, and we had this observation that this mapping lambda gives a log of expectation of exponential lambda dot x, that this is a convex function. It's by Hölder's inequality. And so just by this lemma, the function Fn is convex, okay, because it has exactly this structure. Okay, except there's a 1 over n in front of it. And of course, Fn converges to F, so F is convex as well. So the supremum of convex function. No, that's not true. So we know in advance that, no, yeah, it is. Yeah. It's the supremum of affine functions of T and H. So it's also clear that from the formula that it's convex. Okay, and yeah, one more observation I want to do is that, so let me put it somewhere in the margin. So we said that DHFN, this is the mean magnetization. Okay, and the sigma i's, they are between, they are either +1 or -1. So this derivative is bounded. Okay, so if I worry about convergence, I know that in any case this derivative stays in a bounded set. Okay, so because the functions are convex, I can write for every h prime Fn of, so I'm going to look at what happens in a neighborhood of h. So I'm going to move it by h prime. Fn of t h plus h prime, because of convexity, this is always larger than the tangent at h, which is Fn of th plus the derivative of Fn times h prime minus times h prime. Right? This is by convexity. And now, so I'm wondering about the convergence of this derivative. We said it's bounded, it's between -1 and 1. So up to extraction of a subsequence, I know that it converges to something. I just want to say that there's a unique possible limit point. So let's say that along a subsequence, it converges to something. Let's call it P. Okay, so say that it's bounded. Converges to P along a subsequence. In order to conclude, I want to say that P is the derivative of F. So if I pass to the limit in the inequality I wrote along this subsequence, I get, so, and moreover, let's say, for every h prime, f of t h plus h prime is larger than f of th plus ph prime. Okay, so I found an affine function. This function f of th plus ph prime, it's an affine function of h prime, which is always below the function f. So if f is differentiable at h, this is only possible if p is the derivative of f. So since f is differentiable, at th, this is only possible if p is equal to the derivative. Okay, I could write it a bit more step by step, maybe by saying that, you know, f of t h plus h prime, this is equal to f of t h plus the derivative times h prime plus little law of h prime. By using comparisons. Okay, so I'm just leaving it like this, but I hope it's clear. So that's the end of the proof. Maybe I'm going to mark it like this. Yes, so indeed, this is true for any convex function. If you have a sequence of convex functions which converges pointwise, then anywhere where the limit is differentiable, the derivative will converge to the derivative. It's nice. Okay, so now we know how to answer our questions about this mean magnetization. Because we know from its observation that it suffices for us to differentiate this limit. So let's think a little bit about what this limit function does. Maybe I'm going to rewrite it. So now recall f of th is the sup over m of t m square plus hm minus psi star of m. And let's suppose that let's focus for now on the case h equals 0. You know, when there is no magnetic field. Maybe ultimately I want to understand a small neighborhood of h equals 0, you know, because at least in the experiments of Curie, this is where the discontinuity was possibly arising, depending on the temperature. So let's for a second just set h equals 0. And think about this function tm square minus psi star. So if you think about this function psi star, it looks sort of like a parabola. So shape of this function m gives tm square minus psi star of m. So for t small, the fact that you add a little bit of tm square will not destroy the fact that minus psi star looks like a downwards parabola. This function will look like something like this. Okay. And so the optimizer will be at 0. Yeah, and I should have said, how do you figure out the derivative from this? So, okay, so let me finish with just finding where the optimizer is, and then I'm going to explain how you deduce the value of the derivative from that observation. So for now, we focus on where is the optimizer of this function. So for t small, I say that it's at 0. But for t large, initially we had this minus psi star, which was a downwards parabola, or at least it's not exactly a parabola, but it has the shape of a parabola, roughly. And we're adding a parabola, which as t increases becomes more and more sharply peaked. So at some point, this will start to dominate near the origin, and it will create a bump around the origin. So for t sufficiently large, the function will start to look like this instead. Oops. You see, this t m square is going to create some cavity at 0, let's say. And therefore, the optimizers in this case, there will be two perfectly symmetric, and they will be here. So now imagine you're looking at the situation where h is extremely tiny positive. So the function you care about now is the same, but plus hm for a tiny h, let's say positive. Then you're just bending a little bit the curve on one side. So when t is small, nothing major will happen. But when t is large, it will actually select one of these 2 points. So for h positive, you will be here, and for h negative, you will be here. Okay, and it is this jump in m which creates the jump in the derivative. Okay, so now I have to explain this a bit more. So okay, so there's a statement oftentimes called the envelope theorem that tells you that, well, in particular, if there is a unique minimizer in your problem. So for h tiny positive, there is a unique optimizer. Then the function is differentiable, and the derivative is obtained by just naively pushing the derivative through the supremum. So wherever, let's say if unique optimizer M0, then DHF of TH is equal to what we obtain when we differentiate in H inside the supremum. And so it's just M. So we get M0. Okay, so this is, so the fact that the optimizer has a jump when we move from H small positive to H small negative is responsible for a jump in the derivative. Okay, so what this observation says is that except for very special situations, the optimizer is in fact the mean magnetization of your system in the limit of large M. Okay, and this envelope theorem, I'm not going to justify it here, but it's part of the third problem set. I think it's the first exercise. I decided to put it there because I thought it was interesting to expand on it a bit and try to derive the most perhaps the sharpest version of the envelope theorem. But I guess you will find somewhere on the internet more straightforward versions. Okay, another way to state it oftentimes is whenever the function is differentiable, you can do this passing the derivatives through the supremum. Are there questions? So I consider that, perhaps I was a bit quick, but I hope that I convinced you that we have a way to completely solve the Curie-Weiss model using large deviations. Okay, because we identify the free energy, then we know the convergence of the derivatives, except at extremely rare points. where in fact the limit is not differentiable. So okay. And we can, we have an explicit formula for the limit, so we can compute these derivatives. Okay, and also in the you will explore more of these, more aspects of this formula. In particular, justify the things I said, the fact that when t is small, there's only one optimizer, then it's split into two, etc. So yeah, that's the plan for the third problem set. So I'm not going to explain it too much here. Are there questions? Maybe it's a good time for a short break. So maybe we can take a 10-minute break. Yes. So there's a question about are TNH fixed when I speak about the optimizer. So yes. So if I should write it like this really. So let me try to move this around. I should write M0 of TNH. And so for any fixed TH, if in this problem with the supremum, you have a unique optimizer, which we can call M0 of TNH, then this formula is true. Maybe I'll get myself a glass of water if you don't mind. So there's a question about whether I use H prime, whether this is for this proof for convex functions. Does it assume some sign for H prime? And it's important that you can go both ways on both sides, because otherwise you would only infer one inequality between possible limits and the true derivative. So, okay, let me try to clarify this. So let me, I'm going to expand upon these two observations. So we have this, how do you say, expansion, and we have this inequality that valid for every H prime. And I'm going to perhaps take one more minute to explain how you conclude. So let me, so if I relate the two, I will get, I'm going to say that the right-hand side here is larger than the right-hand side here, and then the FTH cancel out. Okay, so I'm going to write the conclusion of this computation. It's that DHF of TH times H prime plus little o of H prime is always larger than or equal to P H prime, and that's it. Okay, and I want to argue that P has to be the derivative. So what should I say? Okay, so maybe I'm going to rewrite it like this: DHF of TH minus P times H prime is larger than or equal to little of H prime. Right? So you see that if I have a contradiction, if I'm allowed to, I mean, I have to have that this guy is 0 if I'm allowed to have H prime go both on the positive and in the negative sides. Because if I only have H prime which goes in the positive direction, then I would only know that the quantity in parentheses is non-negative, right? Yeah, so there are questions about the envelope theorem. Okay, so let me. Yeah, it's not a very difficult derivation, but I'm afraid that I'm going to blunder it if I try now. So, yeah, okay. It's done in the exercise in the problem set, and if you struggle, we can discuss this next time. But in general, the behavior of the derivative is the supremum of all the. I'm not going to explain it well, but. So the thing that happens if you have two optimizers is that the differential at f will be the supremum of the differential that come from different optimizers. So, you know, if when you look at 1m, the derivative looks like this. So you see, when there are two optimizers, maybe it's interesting to discuss what happens when you have two optimizers. So when h equals 0, you have two, and t is large, you have two optimizers in your problem. And the claim then is that the first order behavior is given by the soup over these two optimizers of the differential. So it's when you go to the positive, the function will look like this in this case. And if you wonder about the differentiability here, this part will come from the M0 positive solution. And this part will come from the fact that minus M0 is also a solution. Okay, so in general, you have this formula that says that the first order expansion is described by the soup of these first order expansions of around every optimizer. And in the case when there's only one, then it simplifies and we are happy. That's the gist of it. All right. So yeah, in general, my attitude is that the central task of the series of lectures is to figure out how to compute the free energy, or the limit free energy. And in some sense, I subcontract perhaps to you in the exercise sessions, or perhaps to future research if the problem becomes hard, the problem of analyzing the limit once we have found it. It should be simpler in principle, or at least it's a separate problem. My goal is to figure out how to identify the limit. So yeah, I kind of of course, I want to convince you that once you have identified the limit for energy, you learn good. But I don't want to emphasize too much this aspect, so I'm kind of willing to push a bit this aspect onto exercise sessions. But of course, yeah, like if you struggle with this problem set, we can discuss it. All right. So now I want to continue with query-based models and continue with using large deviations, but I want to generalize to yeah, I want to consider a larger class of models in the spirit of query-based, and it will come about somewhat later. I'm sorry. I kind of mentioned a little bit in the introduction why I think it's interesting to look at these generalized models. Is because when you don't use large deviations, there are very special things that happen with these more general models, and I think they are very interesting, and they are really in close correspondence to what happens in in statistical inference, and also perhaps even more prominently in spin glasses. So, okay, I want to discuss these generalized query-based models for this reason, and it will become clearer later. But okay, for now, let's discuss what they are. So I want to generalize the query-based model in two directions. The first point, and perhaps the most important one, is that I want to consider more general types of interactions. But I want to stick with something that's relatively easy to solve with large deviations. So I'm going to assume that instead of having this interaction term, which was sum of sigma I, sigma j, or in other words, sum of sigma I squared, I'm just going to consider that it's a generic function of this sum of sigma I, not necessarily the square. So first direction of generalization, the term 1 over n sum of sigma I squared in the energy. Oops. Is replaced by a generic function of this quantity. So let's say psi of 1 over n sum of sigma I for a given smooth function psi. That's the first bit. And the second bit, perhaps somewhat less important, but which I think is also interesting to keep track of, is that so there was this sum over sigma, which we can think of as having an underlying reference measure being a product of Bernoulli random variables. And I want to just generalize this and decide that it can be any probability measure. Okay, so let's say reference measure, which I was always kind of writing explicitly at this 2 to the minus n over sigma of blah, 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 replaced by a generic measure. Okay, maybe I should say by a generic measure. Pn. So really this expression 2 to the minus n sum over sigma, I'm going to replace by integral of blah 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 dPn of sigma. Okay, so if Pn is this product of Bernoulli measures, then we we recover this something. Yes, so indeed, another way to say it is that we consider generalized PIMS. Okay, maybe they are uniformly distributed over the interval 0, 1, for instance. And I still want to make sure that they are bounded. I don't want to have complications because the sigmas go out of the window. So we assume that this vector of length n, its norm is bounded by square root of n. So dPn of sigma almost everywhere. Okay, so Pn is a measure on Rn. Maybe I should have written here. Okay, so when the vector was a sequence of +1s and -1s, clearly the norm is bounded by square root of n, and I'm going to keep this bound in place. So, for instance, if Pn is a product of independent components which are all bounded, then this inequality is valid. Okay, maybe not with maybe it's like 10 times square root of n, but up to a rescaling, I can decide that it's bounded by just square root of n. Okay, so these are the two assumptions that are in place. And so Pn is given to me for each n. I'm given a measure. And at present, so far, I do not assume any particular structure on Pn. It will come in the statement itself of the convergence of the free energy. So let me state it. So let me say the result. So it aims to be, that's right. So the sigmas are no longer required to be +1 or -1. Maybe they are, for instance, uniformly distributed over the interval instead. Okay, so just to make sure we understand what I'm talking about. So now the free energy of my generalized model is going to look like this. So it's still 1 over n log. And then before I had this sum over sigmas, but I said I replaced by this general measure. So I'm going to write integral. And then at the end, I'm going to write dPn of sigma. And inside the integral, I write exponential of Tn psi of 1 over n sum of sigma I plus h sum of sigma I. And this is against dPn of sigma. Okay, so I hope you all recognize that somewhere in this notation we can encode the original Curie-Weiss model. Okay, we take Pn to be the measure product of Bernoulli random variables, and we take psi to be the square function. Is that clear? Okay, so this is the model we want to study, and I want to. So we discovered the limit for energy for the standard Curie-Weiss model, and I want this statement to cover the limit for energy for this more refined model. So surely I have to assume something about this reference measure, and I'm going to assume that when I set t equals 0, the object I get, this fn of 0h, is convergent as n goes to infinity. And okay, so if you think that Pn is a product measure, of the same, an n-fold product of the same measure, then when you set t equals 0, this term disappears. And you have the expectation under this PN measure of exponential h sum of sigma I. But the sigma i's under this measure, they are independent. So you can, it's like when we were doing large deviations, you can write the exponential as a product, and then you can use independence to factor out everything as a big product of expectations, and then you take the log and you divide by n. So when Pn is a product measure, in fact, this whole quantity, when you set t equals 0, does not depend on n. And it's our good old Laplace transform of a single random variable. Just like our psi was this log of hyperbolic cosine when we were doing Bernoulli random variables. Okay, so just to confirm to you that in the case we already know about, this assumption is kind of obviously true. Okay, it converges because it does not depend on n. Okay, so that's one assumption I want to make. And moreover, I'm going to assume that this limit is a C1 function. And under these conditions, the same formula that we have seen for the standard Curie-Weiss model is also true for this more general model. So then the limit when n goes to infinity of fn of th is equal to, so I'm going to again denote it f of t comma h, which by definition is the supremum over m of t psi of m plus hm minus psi star of m. Okay, so for the standard Curie-Weiss, psi is the square function. That's the formula we got. Okay, and I had written sup over m between -1 and 1. But when we're not inside this interval, it's not difficult to see that psi star is infinite. So whether I write m in R or m in -1, 1, it is the same. So, and recall that psi star is the dual function. Yes, so now I do not impose it, but it's yeah, exactly. It's a consequence of the fact that psi psi will be a one ellipse. So okay, so let me explain this I'm going to start with the proof of this result, and as I start the proof, I think this point will be clarified. That nothing happens when m is outside of the interval. Are there no questions? It's good. Okay, so now I'm going to, in some sense, the proof should be along the lines of this semi-heuristic argument we discussed for the standard Curie-Weiss. And I want to decompose this integral into slices according to the value of 1 over n sum of sigma I. And then large deviations will tell me what's the probability that each of these slices happen, and then I can insert in the exponential the specific value I'm slicing with. Okay, so that's going to be a rigorous version of the semi-heuristic conclusion. Yeah, so for all t, yeah, so for every t, this is for every t and h. Yes. Oh yes, thanks. I messed up the definition of this. Well, yeah, okay. So someone asked if the free energy of almost all mean-field models can be written in this form. It's only the free energy of all of these generalized Curie-Weiss models so far. Okay, so and for the models we are going to discuss next, large deviations cannot be applied, and that's why I'm going to discuss at length how to approach these models using other techniques. All right, let's go to the proof. Yes, so the first observation I want to do is that so it's still the case that when we differentiate in H, this will compute the yes. So I should have introduced. Okay, so let me back up for a second. So this is the end of the, and we just extend the notation with this angular bracket in the most natural way. So now the angular bracket denotes the expectation with respect to this new exponential and this new reference measure. Okay, so now this is, instead I used to write a sum. So each time I had written the sum over sigma, I'm just replacing by this integral. So it's t n psi of 1 over n sum of sigma I plus h sum of sigma I. Okay, and this divided by the integral of exponential of the same exponential. Okay, so it's still true that when we still have dh fn of t and h equals 1 over n sum of sigma I with the bracket. Okay, this is still a valid formula. So we still, if we still do care about this mean magnetization, and it's still obtained by differentiating the free energy. And moreover, so 1 over n sum of sigma I, this is smaller than, let's see, this is smaller than if I compute the second moment. And we said that this is 1. This is bounded by 1. Okay, I assume that this is true. Under so Pn, dPn, sigma, almost everywhere. Yes. So that's the sum of sigma I squared. This is the norm of sigma squared, and I said we assume it's smaller than n. So then I divide by n, and so it's bounded by 1. Okay. I mean, if you want, just assume that each coordinate is bounded by a fixed number, by 1. Okay, and the combination of the two things I just wrote down shows that the derivative of fn with respect to h is always bounded by 1. So Fn is 1 Lipschitz. In H. Okay, 1 Lipschitz means it's Lipschitz and the Lipschitz constant is 1 in the H variable. Okay, and if Fn is 1 Lipschitz, then its limit, if it exists, will also be 1 Lipschitz. So in particular, you see that the function psi is obtained as the limit of Fn 0H. The function psi will be 1 Lipschitz as well. Okay. Yeah, for this inequality, you can think also that if you think that this is an expectation, then you're comparing the first moment and the second moment. So, but yeah, I guess Cauchy-Schwarz is the better answer. Okay. So yeah, because psi is 1 Lipschitz, it's clear that that psi star will be infinite whenever m is outside of the interval -1,1. Okay, because psi of h can only increase at most as fast as h. So if m is, let's say, 2, 2h minus psi of h will go to infinity when h goes to infinity. Okay, and same in the other direction. So psi star is necessarily plus infinity outside of the interval -1,1. Okay, and therefore, when I write this with m in R, if instead I write -1,1, this is the same optimization problem. Okay, so let's go with the proof now. Okay, so the first thing I claim is that the function psi star is continuous where it's on the domain, on its effective domain, which means where it is finite. So I don't really need to use this, but okay. I'm still going to use it. So I'll leave this as an exercise. Let me think for a second. Yeah, okay, it's convenient for me to use this, but I don't think it's necessary. But let's take it for granted. So if it's continuous, then the supremum is achieved at some point, and it's kind of slightly easier for me to argue, like knowing that the supremum is achieved at some specific m, although I could go without this. Yeah, also at the boundary, because the psi star is lower semi-continuous, so you cannot have jumps. Because it's the convex dual of something, it's lower semi-continuous, so it cannot have jumps at the boundary. But okay. Yes, I should not have used that, I guess. But, what I just wanted to simplify a bit the discussion by saying that the supremum is achieved at some specific point, but if you don't like it, you can rework the argument without assuming this. So I'm going to write it M0, but really I should write it M0 of T and H. Okay, so for each fixed T and H, the supremum is achieved at some M0. And now I can use the general large deviation principle we have seen. Okay, I have when I said T equals 0, what we are computing here, so T equals 0, this disappears as we said, and we are computing the Laplace transform of Hn times 1 over n sum of sigma I. Okay, so it's the Laplace transform of n times the mean magnetization. And then we take the log, we divide by n, and the assumption is that this converges and that the limit is C1. Okay, so it matches this large deviation result we discussed earlier. You know, when you have the Laplace transform of your sequence of random variables converges to some limit, and the limit is C1. So by that large deviation result, we know that this random variable 1 over n sum of sigma I satisfies the large deviation principle with speed n and rate function psi star. Okay, and this is what I want to use to complete the proof. So if I write, so let's say denoting, oops. Let's say U epsilon M0 minus epsilon, M0 plus epsilon, like this small open interval for some small epsilon. I'm going to write Fn of T and H is always larger than 1 over n log integral exponential of T psi of n Tn. So here I'm rewriting the definition. But now I'm going to insert the indicator function that the mean magnetization is in this small interval around m naught. So indicator function 1 over n sum of sigma I belongs to U epsilon dPn of sigma. And now, okay, so I just inserted the indicator function. So far, it's clear that the inequality is valid. Now, what I want to say is that because this magnetization is within this tiny interval of M0, I may as well replace the quantities here and here, essentially by M0 up to some small error, which depends on epsilon. Okay, and once I have done this replacement, I am left with just computing 1 over n log of the probability that this mean magnetization belongs to U epsilon. And this is where large deviation tells me that in the limit, this quantity behaves like essentially, at least for large n, this quantity behaves like exponential minus n times the infimum over U epsilon of the rate function. Okay, so in order to avoid writing too many lines, let me just say the limit. Let me try to do these two steps at once. This would be greater than so I will have these guys. Oh, sorry. I use French notation for the interval. I meant this. It's the tiny interval centered around M naught. Yeah, sorry about the. Sometimes I remember French notation for this. Okay, so I want a lower bound. So the worst that can happen is that these quantities, they look like the inf over u epsilon. Sorry, there's a t. And then I'm left with the large deviation part. And the large deviation, what it tells me is that the probability that the mean minimization falls into u epsilon is always larger than psi star of M naught, in fact. In fact, it's even better than that, and you have minus the infimum, but I can just use psi star of M naught as a bound. Okay, so in fact, if I want, I could even insert minus the inf over u epsilon, but this is a weaker bound, which is sufficient. Okay, so that is true. And if I shrink epsilon to 0, then this inf over m in u epsilon will just become t psi of m naught plus h m naught. So letting epsilon tend to 0, we get liminf n goes to infinity of fn th larger than or equal to t psi of m naught plus h m naught minus psi star of m naught. Yeah, so now that I wrote this, you see that I don't know, it made me feel comfortable to assume that the M naught is the, that M naught exists as the guy who achieves the supremum, but in fact, I can write just what I've done for every M naught. And then once I'm there, I take the supremum on the right-hand side over M and over M naught, and that completes the argument. So I don't need to do this assuming that the supremum is achieved at the beginning. Okay, so let me modify a little bit the argument at the beginning. Let's say we can erase this. It's true, but just to make the proof more agreeable, let's say fix M naught. Okay, let's say in the effective domain of psi star. And then the rest it works. Okay. So then the rest works. And then here I can take the supremum. Oops. Okay, so I have one bound proved. And the converse bound is really very much the same. Okay, I just use a large deviation in the other direction. And so let me do this. So now for the other bound, maybe we can say I'm going to slice the interval between -1 and 1 into slices of size 1 over k, and then analyze each slice one at a time, and then let k go to infinity. So fix an integer k larger than or equal to 1, and write so fn of t and h is larger than, so I'm going to write 1 over n log. Now I split my integral into pieces, so let's say like this. And then indicator function 1 over n sum of sigma I is in my little slice. Sorry. So it's little k minus 1 over big K, little k over k. Yes, sorry, I made a mistake. I mean this down. Thanks for being more alert than I am. And then, okay, there's dp and sigma, which I have to write down in the corner. Okay, so I use the closed interval because this is how large deviations is coming. I mean, it's not important. I could just write equal and okay, fine. Okay, then I would have to deal with -1, 1. Okay. Anyway, this inequality is okay. And so now we have a finite number of terms, and each will behave like exponential of n times some number. So you see that again, this maximum over this k, or maybe 2k different numbers will show up. Okay, so the lim sup as n goes to infinity of fn of th will be smaller than the maximum of all of these quantities we observe. So there will be. So now I'm doing the bound in the other direction. So when I try to substitute this guy by its value, I have to think about the largest possible bound. So I'm going to write the sup of t psi of m plus h m over m in the relevant interval, k minus 1 over k, k over little k over bk. And then there's the large deviation guy, which I can compute at k over n if I want. So it's going to be minus. No, this is a. No, yeah, sorry. So here I have to write minus inf over m in k minus 1 over bk, k over bk, psi star of m. Okay, now I claim that when you take capital K going to infinity, well, okay, clearly this supremum will just, psi is continuous, so you will just start to see something extremely close to evaluating the function at little k over bk. And here, yeah, perhaps I'm running a bit short of time, so I don't explain very precisely why things are fine for psi star, but psi star is continuous, at least in the entire of what's defined. So in the end, I actually want to use this thing. And okay, at the boundary, it's going in the good direction for this bound. Possibly psi star is becoming extremely high, but okay, you don't need to worry about this. Okay, so as k goes to infinity, I claim that this shows that the same thing is true. So lim sup Okay, so this proves the converse band. Okay, so I'm running short of time, but this is really the main results I wanted to present today. So to summarize, we studied the standard Curie-Weiss model and then the generalized version of it. And using large deviations, we figured out what is the limit for energy. We also saw that once this is obtained, we can infer the behavior of the mean magnetization by taking derivatives, because we have this nice property that the limit of the derivatives is the derivative of the limit, provided the limit is differentiable at the corresponding point. And when you study these more general Curie-Weiss models, really plenty of new phenomena can occur. For instance, you can cook up a model which has no phase transition. For instance, if you take, for the psi function, if you take minus x squared, then there will be no corner in the derivatives. You can also create situations where you have a jump in the mean magnetization. So this I have not explained, and maybe you will see it if you go far enough in the problem set. But for the standard Curie-Weiss model, when we enter the paramagnetic phase, the mean magnetization, this, okay, when we are at the critical temperature, the curve passes through the origin, and just above it, the curve starts to look like this, but it's just a tiny jump. But in the more general models, you can create jumps which are immediately macroscopic. At the discontinuity, boom, the magnetization becomes away from zero instantaneously. And yeah, so I don't have enough time to explain all of this, but yeah, so you can play with lots of different functions. In particular, if you look at psi, which is essentially the indicator function of some piece, you can recover. You can see more directly the link with large deviations, I guess. All right, so okay, maybe this is a bit too much to say. So the overall message is, using large deviations, we can conclude for these models. But this is a very special circumstance. For the other models I want to discuss, we will not have this large deviation tool available for us. So we'll have to devise new tools. And before we go to the more complicated models, I want to devise these new tools for this Curie-Weiss model. Okay, so I want to find an alternative approach that also gives us the result that we saw today. All right, so sorry I was over time, and thanks a lot for your attention. I'm happy to take questions if you want.